All right, so there's been some concern about the homework assignment, so let's talk about a few of the things that you may encounter. Here's my solution for problem number one. I've got a picture. It doesn't show, but I should put up here that my coordinate system is at the top and it has positive down and positive to the right. Made my list of knowns and unknowns. Part A asked me for the time, and we usually use the Swiss Army equation in Y to find the time, and I was able to do that. Then it asked me for how far, and we usually use the Swiss Army equation in X because this last term here goes to 0, and that's very simple multiplication. Then the big question was, what's the vector velocity? When you're done, you're going to have two components of velocity, X and Y components of velocity, but you need to put them together to find the resultant and the angle. So here I know that my final x velocity is the same as my initial, but what is the final y velocity? So I went over here and used the simplest equation to find it. V final y equals v initial y plus a times t in the y direction. V initial y is 0. AY is the acceleration due to gravity, and there's my time. So I found an answer that was really close to 54. I could keep 53.9, but there you go. And then I used the Pythagorean theorem to find the resultant velocity, which was because one number is small and the other is very large, it's dominated by the large number. So it was 54.6. And then to find the angle, I used inverse tangent of the y over the x. That's because when we land, we have an x velocity of 8 meters per second, but this really huge y velocity of 54 meters per second. So this angle right here winds up being very large. Okay, that's not too difficult. The classic number one is also what problem two is all about. Only here you're given the time, and that's pretty cool because that makes you more flexible. So here's all the list of knowns and unknowns. Again, this is normally something we know, but this time we don't. And so the first thing they ask is, what is this number that we don't know? And since it's in the y direction, we should use a y equation. And since we don't know the final y velocity, we should use the y Swiss Army equation. And so the final y is all that survives out of delta y because the initial y is 0. And that's going to be equal to 1/2 of the acceleration in the y direction times the time squared. And that winds up being 33 meters. How far does she land away from the edge of the platform? We'll use the x Swiss Army. Again, this last term turns into 0, so it's just the x velocity times the time, and we get this number. That's fairly simple, just showing you that when they give you the time, things go a lot faster. Okay, question number 3 is a classic number 2 problem and pretty straightforward. But after we draw our picture, and I didn't indicate, but I probably should, that the coordinate system that I'm using has the origin here, and that positive is to the right for x and positive is up for y. We have an extra step, and this step is actually part A, and that is to componentize this initial velocity into its x and y components. So take the original velocity times the cosine of the angle to find the x component, take the original velocity times the sine of the angle to find the y component. Those go into the list, and then we can start solving things. A typical first thing we solve for is the time. We use the y Swiss Army equation. And the next thing we solve for is how far it goes, and we use the x Swiss Army equation. I'm guessing that you guys are pretty good at this so far. But that brings us to number 4, which is a classic number 2 with a twist. We aren't given this number. So when we go to do our componentizing that you have to do first, we have an unknown number times cosine of 45. Now cosine of 45 is 0.707. I did that in my calculator. And sine of 45 is also 0.707. So when it comes to these initial velocities, I don't have a number, but I do have an expression. So if I just go ahead and do the same steps that we normally do, like use the Swiss Army equation here to find the time, we're going to get stuck. We're going to get stuck with an equation that no matter what I do still has time and this unknown in it. So we're stuck there. Let's try the next thing we normally do. We normally try to find the distance traveled. And in this case, we have a little more information because we know it goes 98 meters. And of course, this term right over here turns into 0. So we have 0.707 VI times T. And again, we're stuck again. But we're stuck with an equation that has the unknowns of VI and T, and this one had the unknowns of VI and T. In other words, we have a system of two equations with the same two unknowns. Now, I had some missteps in how I got started. I didn't know which one I wanted to solve for first, and I wound up solving this one, which looks easier. I wound up solving it for 0.707 VI. And I did that because 0.707 VI also appears in the other equation. So 0.707 VI turns out to be 98 over T. I put that in place of this one in the other equation, and then I had an equation with just T's in it. And I solved for time, and I got 4.47. This may not have been the most intelligent thing for me to do because the question asks you not for the time, but for how fast it was shot. So if you are more clever than I, you would solve this one for time, put the time in here, and then you would get this answer right away. But I got 31 meters per second. So what we're doing here is we're showing you that the method that we use is bulletproof, and it can help you find the answer even when you don't have all the information. Let me just say up front, not knowing the launch velocity of a projectile is one of the most difficult things in the world. It's really hard logically to solve for what was true at the beginning when you kind of know what's true at the end. So I know that if you got stuck, it probably didn't seem like you knew which way to go, but just do the steps that we do. Try these things, get as far as you can, do the other steps, and then see if you can recover like we did here with system of two equations and two unknowns. Number 5 was kind of difficult because the first thing we asked about is this at the top of the trajectory. So I went ahead and componentized the original velocity. It's at 60 degrees, so the x is smaller than the y this time. And then I set this up, and the trick here is if you want to find this maximum height, you have to set the final y velocity to 0. That is what's true when the thing is at its peak. Now, you don't know what y that is, you don't know how high it is, but I just called that letter h for height, the maximum height. And I'm going to try to solve for that. Now, if you do try to solve for it, you're going to be using all of the y equation stuff, and you're going to find that you have a 0 here, and you don't know this thing, and you don't know the time. Well, this is the one you don't know and you're looking for. This is the one you don't know and you're not looking for. So why not use the no time equation? And this is the no time equation I wrote right here. And then I put the numbers in, and I was able to solve for h. It's a pretty big number, 7,760 meters. That's miles high, and it's kind of absurd and kind of okay for artillery, especially aimed at this angle, to go that high. It's going to go much higher than it is going to go far. Then the next thing it asks for is to find the time to get to the maximum height. So I went ahead and put VFY here as 0 and 390 as the starting velocity, and I found the time to get to the maximum height. And then when we want to find the final velocity, we can prove this in class. We can do this in class. The final x velocity will always be the same as the initial, and the final y velocity, when you let the problem go all the way from one end to the other, you're going to find that the y velocity reverses itself, and so it lands at minus 390 meters per second. So if you draw a triangle of the x velocity and the y velocity upon landing, you'll find that it's a triangle that looks a lot like the triangle of the x and y velocity at launch, except that this angle is below the horizon, this velocity is below the horizon, and you'll get the same resultant. So you're going to land with 450 meters per second, but 60 degrees below horizon, or negative 60 degrees. Ooh, you can't even see my pencil. This thing is on it's on refocus patrol. Okay, and finally, we got the this one, and we'll go over this in class. This is the riverboat problem, and I showed you there were 2 ways to solve it, and we'll talk about that. All right, quick little video just showing you what's going on with the homework if you get stuck.